We are coming to the last part of chapter 5. So I will want you to do the remaining questions on your question note and pause the video now. We'll check the answer later on, one by one. Okay, so let's take a look at the first question. Though. For the first question, it's very simple, just using the hands rule. So if you try to look at the question, it said first of all, the most important thing is you should pay attention. The charge is actually positive charge. Why? Because if you find out it is negative charge, then you should realize that negative charge velocity and current should be opposite, because this is how we define the conventional current and the electron flow. But here, since it is positive, then it's easy, because for positive charge, the current and the velocity of the positive charge is simply the same direction. So it's very simple. If you try to simply use the hand rule, which in this case, if you recall, it should be left hand rule instead of right hand rule, then simply these are the answers. So for the first three, it will be B field going into paper. Part B is force going into paper. Part C will be the force going out of paper. And for the last two, it will simply be no force, because you can see that the two vector here, they are either I should say they are all going on the same axis. Alright, these two they are opposite. These two they go in the same direction, or in short, they are the same axis. And in this case, there will be literally no force. Alright, literally zero. In a case where you have like at a certain diagonal, let's say this is like B and V, then there's still a chance you may have it, because you can still decompose it. For example, the B field with a vertical component, and you can still deduce it in that case. But for cases like these two, there's no way that you can have any force. The force is literally zero. Okay, so for the next question, I would like to I try to show you from the beginning again. So first of all, once again, you have to pay attention. There's a charged particle, and you have to make sure what charge it is. So it is positive charge. So like we said, it will be easier because it will be the same as the direction of current for the velocity. The next thing that you want to do is this time they don't provide you the B field directly, but they provide you a magnet. So by looking at the magnet, then you can see the external B field direction, which you know for a usual magnet, it goes from north to south. So north to south. So in that case, by looking at the position of the the proton, then you know the B field, if I were you, I will draw it out, going to the right. Okay, and then you can determine the force by looking at the velocity and B field. So for the first one, then you should find using the left hand rule. So FBB is right, I is up, this is I, just so you know, and so the force should be going in, so across for F. The next one, apparently since they are both going into the same direction for I and B, so there's once again no force. For this one, FBB is going to the right, I is out of paper, so force would be going up. Okay, so this is how you could do it. Should be very simple. You can even solve it in year 10. Let's take a look at the next question. It said electron with speed v enter a region of magnetic field B normally. Normally means that it's 90 degrees, so you have less to worry about the angle. And deflect in the circular path as usual. Deduce expression for the number of revolution per second that would make. So first of all, I think you need to get yourself clear on what they are asking. It would be the best if you can try to use a symbol to represent it. So what symbol would it be? Number of revolution per second. So basically this means frequency, because frequency means how many cycle per second, right, in hertz. So if you see this, then you can then start to produce the equation, and that would be like how we usually start with F equals to ma for circular motion. So centripetal force, centripetal acceleration. Force would simply be BVQ, because angle is 90, so we will just simply skip it. And mass for the electron, of course. And for the acceleration, you have many choices. So I would be the best if you could simply look at the data booklet, which you learn in chapter 6. Okay, so you want something to do with frequency, and you don't find anything here, because if you remember, there are 4 kinds of form of centripetal acceleration, but not all of them are here. But if you remember what you learned in chapter 6, I told you that you can actually deduce it from the data booklet, which is this one. Alright, I'm making a circle with here, because well, maybe I'll just copy it here first. So 4 pi square r. Alright, here 4 pi square r over t square. Alright, is one of the 8. But then since you know 1 over t is frequency, then you could have 4 pi square r frequency square. So then you can substitute it here. I will put it down. 4 pi square r frequency square. And you want to express with f as the main term. So f as the main term. BVQ on the other side, and then all these things float to the other side. M 4 pi square r, and then there's square, so I'll have to root the whole thing. And I think that's it. If you like to take the pi outside, that's fine too. Okay, maybe I'll do it. BVQ M R. Okay. And part B. Electron is replaced by proton, suggests whether answer in A would change. Nothing. I don't think so. Because when you change to proton from electron, what would be changed is simply the charge Q. It goes from negative to positive, so it would affect direction. But in terms of number, it will not affect anything. And I assume the V is the same, B is the same. Mass, of course, it will change. And radius may be changed in that case, and frequency, okay, may be changed. So I think, well, I think how about this? I actually don't know what exactly they're asking. Are they asking whether the frequency will change, or are they asking the expression will be changed? In terms of expression, I'm sure that the expression will still be the same. But then if you say, hey, if there is a frequency for electron and now we change to proton, would it be different? Then let me try to deduce. B is the same, V is the same, Q is actually the same, mass is different. Mass would be higher for proton. Radius, actually it depends, I would say. Actually, I don't think we should do this. Should we actually do 2 pi? It would not be good, because you don't know what happens to radius, because there are 2 unknown here, right? So it might not be good to deduce that. It might be better if you see, cos V equals to 2 pi r over t. Wait, if this is the same, then these 2 should remain the same, right? I mean, the product of them remain the same. They might have both increased though. They could, but is there any other way to know? I don't think so then. Yeah, probably not. There's no other way we can do. So we actually don't know what happens to the radius and frequency, because they might get both higher, or they can actually get both low, as long as the ratio is the same. So I don't think we can know about it. Oh, but I realized that we can actually do something to do with V and R here, right? Because V in itself has a relationship with R also. So maybe we can further simplify this expression in part A. So since, as we said, by definition, V is 2 pi R over T, then that means you can also say V is 2 pi. Oh, shall we actually redo the whole thing? Maybe it would be even better. So let me just quickly redo this expression. All right. So V is 2 pi R over T, and that would also mean 2 pi R times F also. So we could actually substitute this into part A. B 2 pi R F Q M 4 pi. Just copy this, and then we should find the F cancel out, the 2 pi cancel out, and R would cancel also. So we actually can find that it's independent of R. So that's why I feel a bit strange just now, like it shouldn't be like that. Anyway, so we left with BQ M2 pi F. Oh, so it's actually even more simpler. So we could have F equals to BQ over 2m pi. So that means if this is the expression for part A, and for part B we are thinking about whether changing to proton would make a change, then it should be now more obvious. B is the same, Q is, in terms of magnitude, the same. It's just change the sign from negative to positive, so we change the direction. And then mass is now higher, pi of course doesn't change, and so in that case frequency will be lower. Okay, so frequency is actually lower, and that is what we find. And that actually means if you try to further deduce by looking at these and V, because V doesn't change according to the question, then frequency decrease, then that means radius would increase in that case, right? If this is the same, and yeah, and this R would increase instead. Okay. Okay, next question. So it said there's two parallel plates, as you can see, positive and negative here, and the electric field is directed from top to bottom, and I think it will be the best if you can try to draw. Actually, they don't have to say, because you know electric field must go from positive to negative, and has a magnitude of this. The shaded region is a region of magnetic field normal to the page. Okay, so you don't know whether it's into paper or out of paper. It said deduce the magnetic field strength and direction so that electron experience zero net force when shoot through the plate, okay, with a certain velocity. I think the velocity, does it matter? Yeah, it doesn't matter actually. So it's not that difficult actually, but it's a very typical classic physics question we want to solve in the past. So we have two forces. When these enter the region, we have two forces. One must be going up, one must be going down. And from the electric field, you know this is proton or electron. This is electron. Oh, I almost missed it, right? Because it's very important. This is electron, so think about which side would it go to. This is positive, right? So that's why it will got attracted upward by the electric field. Okay, so let me label this as Fe for electrical force, electrostatic force more precisely. And then if you remember that, then electrostatic force, you may be thinking about, hey, so could we use this equation, Q1 Q2 over R square? The answer is not, right? You cannot use this one. The reason is that even if you know the charge of these, like Q, positive, negative Q, like this, you still cannot use it. The reason is that for the Coulomb force, this is Coulomb force, it is only referring to 2-point charges, the force between 2-point charges. However, this is a parallel plate. Parallel plates are different. Parallel plates are like this, right? So this is the electric field. Point charge is like this. They have different electric field. So like this. Alright, and apparently they are, totally different pattern, and therefore you cannot use the Coulomb's law to estimate the force. So then you may ask, so how could I do that? Because apparently you can see they provide you the electric field strength, then you can actually use it. You can see Newton per Coulomb. So the equation that you need to use is E equals to F over Q, which equal to 2.4 times 10 to the power of 3. Okay, that is something you will need to use. This is Fe actually. So what is the force that pointing downward? Then that will be the magnetic force. And I call it Fm here, because that is due to the magnetic field over here. And since the question asks you about the direction also, then you have to deduce. If you have a force that pointing down, you may want to use your left hand for the left hand rule again. Force is going down, B field is unknown, and then for the I, again be careful, this is electron. Velocity going in the right direction, that means the current going in the left direction. So F is down, I is going to the left, so B is going into paper. So for should I say the direction, maybe I'll just write here, B field direction is pointing into paper. Okay, and for the force F magnetic, it will simply be BVQ. Okay, so in order to find out the magnitude, that apparently we have to relate to two equations, since we know the information that the net force is 0, and so we could simply put Fe equals to Fm. You may say net force is 0 because net force is 0. Okay, and then you just find out the expression, which for Fe it will be E times Q, and then for Fm it will be BVQ. Alright, so the expression is actually quite clean, it's quite direct, and you should find the Q will cancel each other, leaving you with E and BV. And in fact they gave you the values already, so we can just substitute it. For B it is unknown, for V it is given 2.0 times 10 to the power 5. Just double check all these things are in SI unit, so it will be all good, and therefore you should use your calculator and find out B is 1.2, 3 minus 5, so 10, negative 2. The unit is T, Tesla. Okay, so this is how you can do part A, which is quite long. Okay, so let's take a look at part B. It said suggest whether the proton with the same speed would also experience a 0 net force. So let's think about this. From the direction, first of all, you may see that if we try to have, maybe use blue color, if you have a positive charge here, what will happen to the electric force Fe? It will be opposite direction, Fe, like this. right? Because you change the charge simply, right? So the electric field or this proton will be attracted towards the negative side of the plate. At the same time, the Fm magnetic force, it will also be opposite direction, because simply that's what you learn in year 10 also. When you try to apply the flaming left hand rule, if one of the B field or current is reversed, then the force is reversed. If both of them reverse at the same time, then force will remain the same. And here, apparently, is simply the current opposite, because now you change the proton. So the force now is still opposite to each other, which is good. That means there has a chance to be cancel out each other. So then what next you need to do is look into the equation, which you actually did it in part A, where it is E equals to BV. So by seeing this, or you can try to see if this is possible, like could E equals to BV, then you should find it could, because this is what we find out also earlier, that E does really equal to B times V, as when we change to proton, electric field doesn't change. I mean, this is set by the question. B field doesn't change and V doesn't change also. So this is all good. So that means for answer in question part B, the answer is yes. Alright, the answer is yes. That means it was experienced zero net force. Part C, very interesting question. Actually, I like this question very much. It said the electron speed is double. Suggest whether the electron will still be undeflected for the same magnetic field found in A. So let's take a look at these. In part A, what we find is, or back to here, we have two force once again. So for one of the force, it was Fe equals to E times Q. So when you double the speed, it has nothing to change. But for magnetic field, because it is BVQ, so if you double the velocity, then you will simply double the magnetic force. Okay, and so that would actually means it will go faster and faster and faster. Okay, and that means it would not be balanced simply. If you try to draw the free body diagram on the electron, the Fe will still be the same length, but then for Fm, it will be double the length. Okay, so yeah, so simply that is how it will be done. So since the question already told you that B field is remain the same, right? If you really want to maintain it the same, then what you can do is you may say you cut the B field strength to be half, then yes, it could be restored to have zero net force if you want. Okay, so for this question, it's simply it would be deflected, and it will also be deflected towards the bottom also. Okay, very interesting question. Let's take a look at the last question. So here we have a long wire. I think we have a current that run through this, and then the magnetic field, right, is known, and I suppose it is perpendicular because it sets the direction of the wire is north to south, but then the magnetic field, it is, I think it simply just take it as the 90 degrees, that one. Oh no, not really, 30 degrees, sorry, 30 degrees below the horizontal. So calculate the force experienced by that. So for this question, I think it's simply applying the equation F equals to BIL sine theta. If you really want to check it, I would say makes 30 degrees below the horizontal. Below, so this is horizontal, this is 30 degree, and then you actually it should be a 3D diagram, so not very good. Here is a wire, is a current. Okay, and then yeah, so you have to take the one that is literally 90 degree, which is the horizontal, that one. So for this one you should actually take actually both would give you a force. Should it be the one going in this direction? Oh, actually no. No. Not this picture. I draw the picture wrong. Okay, so I think what it should is cause it go from north to south, right? So the wire go from north or south to north, doesn't really matter. But then the horizontal and also the B field should also be north to south or south to north also. It doesn't really matter the direction. In this case, we don't need to determine it. But then this is a horizontal, which is the same path, but then the actual B field is 30 degrees below the horizontal. So the one that is the component, you can imagine there are two components for this B field. It has one that is parallel with the eye. There's one that is perpendicular to the eye. So we actually want to find out this one, so which is B sine 30. Okay, so B sine 30 is really okay, is really correct one. Okay, so finally we are confident to move on. So force equals to simply multiply all of them together. I is 3000, L is 30. Alright, sorry, I'm lazy to write the 0, but then in exam you should write it down and then you just multiply them. Okay, so I have find 225,000 times 10 negative 5, 1 2 3 4 5, so 2.25 meter, right? Yeah, all these are in SI unit. Oh, not meter, sorry, Newton. Right, we're calculating force. Okay, so this is how you could do it. In fact, this is a pretty large force also, but luckily I believe for a length that is 30 meters long, it should be quite heavy. So these 2.25 Newton would not be observable unless you use a really light wire. But then if you use a really light wire, I don't think you can have such a high current. I'm pretty sure it will get very hot. Okay, so that is all for chapter 5.